So we're going to import some data from an Excel file and convert that data into graphs so we can better examine the data. The data is basically water molecules passing through a tube, and it's going to take the x and y coordinates and the x and y velocities at 26 time intervals as these atoms pass through the tube. With this we can basically gather information of the forces acting upon the particles and use this to create better filtration systems, which will make it easier for everyone to access clean water. So first off, the household command CLC clear and close, and then all of this here is basically to import our data from the Excel file. We're going to import it as raw data, which is all of the data from the Excel file. This is the location of the Excel file in my computer, the sheet number, and then the range of the data that we want to import. We're going to set all of the non-numerical data and data that just doesn't make sense to R, and we're going to set all of the R data in raw to NaN. We're going to reshape the data, and then we're going to separate all of the data into time steps so it'll be easier to access. Into columns so it'll be easier to access. We want to first find the pressure, so we need density, gravity. Density we're going to assume to be constant. We're using water molecules, so 1 gram per centimeter squared, and gravity is assumed to be 9.8 meters per second squared. We're going to convert density to nanometers because that's how the data was absorbed, and then we're going to also convert gravity into nanometers. We want to sort our data by atom number. That will basically leave us with it like this, and then we're going to get rid of all of the NaNs at the end of the data. It's going to sort the numbers first and then leave NaN at the end, so we get rid of those. And we also we're going to reshape the data. It was taken at 26 timer intervals, so by doing it like this, we'll have ATN will have each atom in a column, and we want to do the same thing with the y coordinates. We want it in the same order so it lines up with the atom numbers. We want to get rid of the NaNs at the end, and we want to reshape it so we'll have all of the y coordinates for an atom in one column. We want to find the height. We need the height for pressure. We're not given the radius of the tube, so we're going to take the radius to equal the max y coordinate, and we're going to subtract that from the y coordinate of the particle at the time, and this will give us the length of the water above it, which is necessary for pressure. We're going to take this height, multiply it by our density and times our gravity to get the pressure. Okay, we're going to plot pressure and mean pressure as a function of time step. To get the mean pressure, we're going to find the mean of this pressure here, and we put this 2 here at the end, which basically means that it's going to take the pressure of each row. So it's going to take the pressure at each time step rather than of each atom. And our data, when we imported our data from the Excel file, it doesn't have the time step in each row for the atoms, so we're going to have to basically create a matrix of ones, a 26 by 300 matrix of ones, and we're going to have to turn it into where they have the time step in each row corresponding to each atom number. And that's basically what I'm doing here. So this first row, for each 300 atoms, it would have the first time step set to it, and then so on. And then only thing left is to plot this. So X, which is our time step data, A and P is our pressure, and for the next figure we're going to take T, because we found the mean. The mean is they found the mean of a 26 by 300 matrix by row, so it's going to leave us with 26 outputs, and then T is the time step, which is only 26 outputs as well, and so that's what that will line up. And then for this one, we're going to find the pressure of the first and last atom as it flows through the tube. So rather than plotting the pressure as a function of time step, we're going to plot it as a function of distance through the tube. Again, we're not given the length of the tube, so we're going to take the length to equal the max x coordinate. And so we're going to sort our x coordinates by row, or we're going to sort our s coordinates in the same way that we sorted our atom numbers, and so the s coordinates will correlate to the atom numbers. And then we're going to get rid of the NaNs at the end and reshape it to the same format as we did our atom numbers. So the first column, or the first column would have all of the s coordinates for the first atom and so on. And then we just want to plot that. This is basically our s coordinates as a function of pressure of the first atom, and then this will be the last atom. We want to find the direction of the pressure of the first atom and the last atom as they flow through the tube. So basically we're just going to find the slope of the pressure as a function of distance through the tube, and we'll plot that on the same graph as this so we can get a comparison, and that'll give us a direction. If the slope is pointing upward in the upward direction, then that means that the pressure is increasing as distance is increasing. And yeah, we can basically just make observations like that. Besides that, we can do a lot of other stuff, like we can show the pressure for each individual atom as it flows through the tube, and we basically just do that by taking the Zan that we found here, but rather than just taking the first column, we just list all of it, and that basically gives us what we need. And that will plot actually 300 lines. And then also we want to find the nice slope of this one too, so we're going to polyfit that into an equation so we can get the slope of that and find the direction of the pressure as a function of distance through the tube. We're going to plot the mass flow. For this one, we want to sort our data differently. We want to sort it by s coordinate, and so we're going to find a new height in order to do that, and that height is going to be equal to it's going to basically correlate to the s coordinates. So as the s coordinates increase, is going to take the height for that s coordinate. And with this height, we want to find pressure, so we're going to take our density that we found earlier times our new height times gravity, and don't need that. Okay, and we also want to get rid of the NaNs at the end, so at the end of the column, so we do that. And we want to take our velocity, because in order to find the mass flow, we need velocity, and we want our velocities to correspond with our s coordinates. So, and then we also want to get rid of the NaNs at the end. We're going to reshape our s coordinates to be a 26 by 300, and that's just because it's easier to work with like that. Take our mass flow, where we're going to find our mass flow, which is density times velocity times area, which will in this case is a circle. And with that, we basically took the sum of the velocities, because we had our mass velocity in a 26 by 300 as a function of corresponding to s coordinates. It's going to take all of the velocities in a certain distance and in a certain distance, and basically just add those together. And we're also going to reshape our s coordinates to correspond with that, and we're going to take the max s coordinate of each row, and then we're going to plot it as that. and it's